Hello class, welcome to part 2 of the Unit 3-1 notes. Now we're going to discover what happens if we have repeated real roots of our characteristic equation. You'll notice that in the previous video, all of the roots of the characteristic equation were distinct from each other, and so there's a very easy way to proceed there. However, now let's naively try that same thing for this one. So we have y double prime plus 4y prime plus 4y equals 0. So the characteristic equation is going to be r squared plus 4r plus 4 equals 0. And you can factor this as r plus 2, also known as r plus 2 quantity squared. And so we have only one root to this equation, but it's like repeated, right? It has multiplicity too, as we would say, because it's repeated twice. And so what that tells us then is naively y should be c1 e to the minus 2t plus c2 e to the minus 2t, right? We just take each of the roots and make them the power of e multiplied by t, right? But you can see kind of a problem here, and hopefully you're seeing this right now. You're just getting the same answer twice, and then nothing really is distinct between e to the minus 2t and e to the minus 2t. So here I guess I'd say you get the same solution twice. The issue with that is, well, what do we know about degree order 2 differential equations? Well, we probably should have two somewhat different answers that we then just add together with a C1 and a C2 in the front. However, that's not really what's going on here. Notice that's exactly the same. And so those two answers, because they're exactly the same, are not what is known as linearly independent. And what we want is we want linearly independent answers. And so when the roots are distinct, that linear independence comes for free. But when the roots are not distinct, like this last example, we kind of have to do something a little bit different. So here's what linear independence means. And if you had linear algebra, this might sound familiar to you. But two, let's say, functions are linearly independent if C1 equals C2 equals 0 are the only constants such that, in this case, let's just use the example we're talking about, y equals c1 e to the minus 2t plus c2 e to the minus 2t equals 0 for all t, and that's important that I say for all t. You'll notice that c1 equals c2 equals 0 are not the only constants for which that's true. I could pick c1 to be -1 and c2 to be +1, and this would be 0 for all t, right? And so these two functions, because, I mean, honestly, they're the same, are not linearly independent. Go back, if you like, to up here, and pick any of these that you like. You'll never be able to find constants c1 and c2 other than 0 for both of them, where you get 0 for all t values. So such is not the case here. So what we actually do, it turns out, and we'll dig into more of this later in a different video, but it turns out all you need to do is to get a linearly independent second answer. So instead of writing e to the minus 2t twice, essentially, you take one of them and multiply them just by a factor of t. And so it turns out then that what we get is y equals c1 e to the minus 2t is good, plus c2 t e to the minus 2t is the other good one, okay? So we just had to add that little factor of t right there. So now let's apply this to the following problems. Okay, so let's work through this first one totally together. So let's first look at the characteristic polynomial. That's going to be r squared minus 6r plus 9 equals 0. if you factor this, this is r minus 3 quantity squared equals 0. So r equals 3 has multiplicity 2, right? Okay. Well, what that says then is that y is going to be c1 e to the 3t. It's repeated, the root is, that is. So it's c2t e to the 3t. And that's all you have to do when you have repeated real roots. Okay. Now, to solve this problem totally, we're also going to need y prime here, right? Because we're going to have to solve for the coefficients c1 and c2. So let's find y prime really quickly. We get 3c1 e to the 3t plus c2 e to the 3t plus 3c2 t e to the 3t. Right? And 5 is what you get when you plug in 0 here. And you'll notice plugging in 0 for t here, this actually goes away. And so I just get 5 equals c1. Okay, that's nice. And now negative 2 is what I get when I plug in 0 here into the y prime. So this whole term right here will go away. And I get 3 times c1, which is 5, plus c2. And so c2 has to be minus 17. And so what that tells me then is that y equals 5 e to the 3t minus 17t to the 3t. And that's it. Okay, coming down to this next one, pause the video if you like and work on it yourself. Here we go. Minus 2r squared plus 16r minus 32 equals 0. I can factor out a negative 2 first, and I get r squared minus 8r plus 16 equals 0. And this factors as negative 2 times quantity r minus 4 squared. The negative 2 does not affect the roots, so you just get r equals 4 with multiplicity 2. And so what that says is that x equals c1 e to the 4t plus c2 t e to the 4t. And once again, we're going to need x prime. So we get 4c1 e to the 4t plus c2 e to the 4t plus 4c2t e to the 4t. Okay. And negative 4 is what I get when I plug in 0 into x, so that's just c1, that's easy. And 3 is what I get when I plug in 0 for t here. And so I get 4 times negative 4 plus c2. And then t0 here is makes that go away. And so I get c2 equals 19. Okay. And so what that tells me then is that x equals minus 4 e to the 4t plus 19 t e to the 4t. Okay, this last problem here, first thing we're going to do is just get everything over to one side first. You always need your second order linear equation to look like this. We get 3r squared plus 6r plus 3 equals 0. Factor out a 3. Okay. So we know that we're going to need x and x prime since that's part of our initial conditions here. 2 is what I get when I plug in 0 into x, for t here into the function x, and so I get 2 equals c1. And minus 2 is what I get when I plug it into t equals 0 into x prime. So I get minus 2 plus c2. And so c2 has to be 0. And so x is 2e to the minus t. As you can see, in the next video, we're going to talk about complex roots. And so probably trig functions are going to work their way into it.